And good start.
Hi, I'm Steve Rostedt. How many people here know of me? Back a month ago, Kate came to me and said, "Hey, Steve, can you come or sign up to the LISA conference? It's going quick, so please sign up quickly. It'd be good to have a Linux kernel maintainer representative there." So I'm like, "Sure." I signed up, and then I get the email with the agenda, and to my pleasant surprise, I'm on it. So that's how I found out I was giving this talk. And then I'm like, okay, what am I giving a talk on? Oh, the real-time Linux update. So I gave a little background in the beginning when we first started introductions, but I'm in 2004, I was one of the first people to work on the real-time patch to help when it started with Ingo Molnar, Thomas Bleichner, Peter Zylstra, and a few others. I contributed quite a bit. The lock stealing, pending owner lock stealing, that was my creation. I also was the first one to create the priority inheritance lock chain with the PI lock. That was actually, I added that. Thomas came in and rewrote it and made it much more robust, but the original code was mine. So I have a history to do this. Now, back in 2017, I left Red Hat to VMware. And basically, I also created this other tool called ftrace, and that became kind of my main job. But since the start of 2017, I haven't really worked on real time. Although I also created the real time stable update. So all those stable branches, I was the one to create that and start. Oops, sorry. So I was like, wait, did we already start recording? Anyway, so I did. I got the stable thing, and even though I don't work on real time, I now work for Google and I work on the Chromebooks, so I don't really do real time at all. But I still kind of, since I invested so much time, I do it mostly on my own time. So I'm even here on my own time. So with that, I am basically, I think, qualified to give this talk. So what's the real-time Linux update? It's done. Okay, I could go home now. It's in Mainline. We started from 2004, and we just got it in September 19th. This is Thomas Gleichner handing Linus Torvalds the pull request, the first pull request done by paper. But hey, Linus, by the way, if you want to know background behind this, it's wrapped in Linus told Thomas, when you send my pull request, I expect it to be wrapped in gold with a ribbon on it. So if you notice, it's wrapped in gold with a ribbon on it. Of course, Linus responded back to him, says, "You don't actually expect me to type this in. I want a real official pull request from you." So what is real-time Linux? So I know a lot of people here probably understand real-time operating systems, but you may not understand what is real-time Linux. Why is Linux considered real-time? Like I said, it started in 2004 with a mandate to make real-time itself a real-time operating system. No microkernels. A lot of times what you have is like Gemini, RTAI, and all these other things that are microkernel within, so basically Linux runs as almost like a guest. And the real-time stuff is done by a little microkernel. So when you want to access it, your application needs to have special system calls to access that. Oh, by the way, I forgot one thing that I forgot my obligatory thing.
You want your selfie?
I have this thing. It's called a camera. Since you guys probably know about cameras here, you can't make phone calls with it. But I've been doing selfies since 1984 with actual cameras. And I was so upset when the cell phone came up. So it's going to be kind of interesting to be able to do the selfie, because I do this before all my talks. But to do it at the place where you created cameras, like the Hubble, the Webb, and Roman, I got to wait. Let me here to get everyone in it. That smile. So there we go. I'm not even going to look. It used to be like I used to take these things and have to send it off to go to phase and have it send off, and 2 months later I get the results, and always came out pretty good. So anyway, back to real-time Linux. So we want Linux, basically normal applications to run on native on Linux and not have anything special. So you could work on your application on any machine, whether it's real-time or not. And then if you really want to start then testing real-time performance, you just bring it over to the real-time patch. So there's back when we talked or first introduced real-time Linux, we had this fight between it's soft real-time. I'm sorry, it's not soft real time. It's hard real time design. Now, a lot of people say you can't make a real time operating system hard real design because it's too big, for it to be hard. You have to verify every single path. I'm sorry, but that's quality. It's not the definition of real time. It's just the quality of the product. It has less bugs. You have to be able to mathematically prove for safety critical Linux and stuff like that, or safety critical systems. You need to make sure everything works right. So you're talking about quality. Once you say to verify all paths, that's a quality issue, not a real time issue. So I always say it's real time design. What does that mean? That means that all needed paths are basically theoretically has a worst case latency and everything works fine. We have no unbounded priority inheritance. But if there's any time that we see something that doesn't fit this, it's a bug. So it's not, it's a quality related. Yes, I'm sure there's lots of things, even with the real-time patch, that you can have unbounded priority inversion and all that, but that's a bug in our eyes. So that's why I say it's hard real-time designed. It may not be actually hard real-time, but it's not soft real-time. To me, soft real-time, if you miss a deadline, you could back up and get out of it. With the real-time Linux kernel, you miss a deadline, that's a bug, the system crashes. So missed deadlines are bugs. So I hate the term real-time anyway, because it's real-time, you hear like, hey, you get real-time updates on your package delivery thing. So it's very ambiguous. I always call it it's deterministic. So I really wish it wasn't called a real-time operating system. I really wish it was called a deterministic operating system, AKA DOS, which was the original real-time operating system. It deterministically crashed when you needed to. So it may impact performance. That's some people when I went to Siemens in Germany, I had a manager come up to me and say, I can't wait till the real-time kernels and, our system's running on the real-time kernel. This is back in 2005. And he's like, to see how fast it goes. I'm like, I'm sorry, it's going to go slower now. But I always say it's the fastest worst case scenario. So if you worry about, outliers, then you want a real-time operating system. So I just say because before I always say, it's not real fast. And like, that's not a really good marketing term. So how could I change it to a marketing term? And I said, okay, let's make it the fastest worst case scenarios. That's what real-time it gives you. So what makes the Linux kernel real-time? Now, I gave a talk, my first talk on real-time was in 2007 at the Auto Linux Symposium. And I also wrote a paper for that with Darren Hart, and it's called The Internals of the Real-Time Patch. If you want to know about it, it's still relevant. It really talks about the technical aspects of what did the real-time patch do to make Linux into a real-time operating system. After I gave a talk, actually, Greg Hartman came up to me and said, Steve, it was a great talk. Now I'm no longer afraid of the real-time patch. So so first of all, we make interrupt handlers into threads. So all interrupts go off, and it could be preempted. Now you can do a lot with that. Once all interrupt handlers are threads, you can prioritize. You can make some interrupts higher priority than other interrupts, where an interrupt handler could preempt another interrupt handler, which isn't the case in normal Linux. It gives you better control of the processing. So which CPU it works on. You can actually now, even though you might have like a hardware issue where interrupts will always go off on one CPU, but say if the applications are running on another CPU and want the interrupt handlers to basically be tied closely to cache locality of the applications running, you can now easily migrate and not be limited by the hardware where the interrupts go off. This is where it goes, same thing I've talked about. And by the way, this was added to mainline Linux in 2.6.39. You have to put in a little option in there to turn it. So yesterday, I think it was yesterday, we had the talk with the Ingenuity helicopter, where the preamp say we didn't need real-time, we didn't use the real-time kernel. Yes, they did. They just didn't use what was not left pulled in. The real-time Linux kernel created ftrace, by the way. It created high resolution timers. It created no hertz no hertz, just the no hertz, where your timer turns off. That came from the real-time patch. People don't realize this. Mutexes that are throughout the kernel, that came from the real-time patch. Before that, it used to be semaphores. But real-time patch needed to have ownership on critical sections. So the real-time patch created a new concept called a mutex. So all those mutexes, that came from the real-time patch. If it wasn't for us, you would still be using semaphores. So a lot of advancements of the real-time of the Linux kernel came from the real-time patch. A lot of times our first testers were musicians, because they said it was the best utility. We installed real-time patch, we could do recording, and we didn't have to worry about the hard drive going off and interrupting our recording or anything. And then later on, I talked to a musician recently before the real-time patch was merged, and they said, well, we really don't need the real-time patch because you guys added so much of your code into the Linux kernel, especially threaded interrupts and all like that. It basically does what we want. So what does that mean by, threaded interrupts? Because obviously in the real-time, in a normal system, you have when an interrupt goes off, that's a hardware thing. Software can't modify that. So when interrupts go off, it basically stops the system. If interrupts are enabled, stops the system and it's going to process. The problem with handling all that within that hardware interrupt context is the fact that the system stopped while you're doing that. So if you have a device driver that has a long interrupt handler, the whole system stalled until that handler is finished. Even if there's other things higher priority that wants to run. I mean, the hard drive could be running, just doing logging or whatever, and you're trying to run your system, that's my problem. So what the real-time patch does, when interrupt goes off, it just masks the interrupt, wakes up the thread, and goes right back to processing. Now later, when the high priority process is done running, it will schedule out and run the device handler. Soft interrupts are also kind of similar to hardware interrupts, but the real-time Linux makes it so that they're run when the thread needs them. Soft interrupts they're just like hard interrupts where they interrupt the system, and it's usually done for network processing, timer processing, block devices. So basically, difference in normal Linux, what a soft interrupt happens to be is just that something that could be preempted by hard interrupts. So that's the difference. I mean, in normal Linux, when a soft interrupt is needed, unless it's disabled, like, like we could disable interrupts, you could disable soft interrupts within the normal code, it's going to preempt whatever you do. And when it runs, it's going to run as long as it needs it. That includes like RCU garbage collection. So it can actually take some time, and soft interrupts do handle up. NAPI in the networking, which is new API. I wanted to extend it and called it even newer API, but that's that also does a lot of things similar to this, but it's also just let the interrupt goes off, but then the processing is done in soft interrupt handlers, but the whole rest of your system, your applications are stalled waiting for all that processing to go. That's the highest priority thing that's going on. So in non-RT, like I said, it runs just like normal interrupts. If there's too many soft interrupts, it gets pushed when they realize that you're stalling the system for too long, then it gets kicked off to something called K-soft IRQD, which is just a normal thread. So then it moves to actual threaded context. So what does the real-time Linux do? What we do in the real-time Linux kernel is whoever raises the soft IRQ runs it in your process context. So it will kick off, you'll run it. So if you get because most times if you raise the soft IRQ, that soft IRQ is doing something for you. So the task will run it, and it will actually be executing it, and it could get preempted as well, and it doesn't stall the system. So there are some soft IRQs actually run from interrupt handlers like networking and RCU. Well, since the interrupt handlers are now threads, the soft IRQs just attached to those threads, so they get preempted just like the interrupt handlers. K-soft IRQD is still there, and actually we make K-soft IRQD a real-time task at priority 1 in the real-time task. I have to look, actually, this is what we used to do. I haven't looked at the code to see if we changed that, but that's what we used to do. So I might be wrong in that case. Now, here's the big thing that when we say, what did the preempt RT patch do? It's this. This was the big commit in there. And what it did was it turned spinning locks into mutexes. So normal spin locks are per CPU. So what you can't preempt a spin lock because it's basically locks the CPU down. And it does when you hold the spin lock, you'll do your processing. If another CPU wants to access that, it just spins, knowing that that process that holds the spin lock isn't going to preempt. So it just has to wait until that process finishes, and then it could, when it's released, it gets it and it goes on, and the next CPU will get it. But these could actually be held for a long time. I've actually measured over millisecond times that there's spin locks in the kernel that can be held for over a millisecond, that means you can't preempt. So if you have an application that's pinned to that CPU and it wants to run, it's going to have a millisecond latency, which is huge in the real-time mode. So to make them into mutexes, we also have to require that it has a hard requirement that we implement the threaded interrupt. That's why that's one of the first things we did, and we got that upstream first, because then we got it out of the real-time patch. We didn't have to maintain it, but you can't make spin locks into mutexes without making interrupt handlers into threads, because there's a lot of spin locks in interrupt handlers. So if you convert the spin locks into mutexes without making them into threads, you're going to crash the system. But there are some spin locks that can't be converted. They're called raw spin locks inside the kernel. And those are mostly have to do with the scheduler or actually the timer itself. There is a few raw. We don't like raw spin locks. Some people say, oh, I got to convert this to a raw spin lock. And we're like, well, do we really have to? Because once you convert it to a raw spin lock, now that's a time you're locked. It just puts it back to the old system where you're locking the system down. But this is also, we had to update lock depth, and there's a new splat that's not very, doesn't articulate what it's complaining about very well. It says you have an invalid context, which people are looking at that like, what the hell is this invalid context? Well, what happens is we actually check that you can no longer grab a raw spin lock and then grab a spin lock after it, because now, like I said, raw spin locks can't be preempted. Spin locks can be preempted now. So, but in the normal Linux without RT, there's no difference. The spin lock and the raw spin lock are the same. So you can have a raw spin lock and then call a function that grabs a spin lock. Well, we have a lot of cases where you turn on some feature and it uses normal spin locks, but it's called from a context that does raw spin lock. So you get this nasty splat. Now we put this in, we changed lock depth before we brought this feature in just to see where it happens. Print K is one of the biggest offenders of it, because Print K uses normal spin locks. So whatever you have a Print K within a raw spin lock, you're going to get this splat. So that's this whole work about, and you've heard all the stories about converting Print K to be real-time friendly. That took a full redesign of Print K, a full redesign. And Linus never liked it. So that's we never actually, if you asked me back in 2005, what's going to be the one blocker that's going to be the hardest to solve putting to Linux, I would have said the spinning locks. No, it was Print K. That it's been like 3 years. The spin locks are all accepted and everything else. The Print K took like 3 years to get in. So, and by the way, this was added to Linux in that picture. That's when this was added. So this is what makes actually this was a key thing to make real-time Linux, preempt real-time into, or Linux kernel into a hard real-time design. Of course, something else we had is priority inheritance, where all mutexes, including sleeping spin locks, have priority inheritance. Now we've added this a long time ago. So for priority inheritance prevents unbounded priority inversion. So user space spin locks was added back in 2006. And to get it in, I had to write the RT mutex design document. So, and it's still there today in the documentation directory tree. Because Andrew Morton said, priority inheritance is very complex code, and he didn't want like 3 people to know it and no one else know it. So he said, you better document this. So actually, there's a full design document on how the priority inheritance work. This is the stuff I told you about that I did, and then Thomas rewrote and everything. So I fully documented it, put it in, got it in mainline, and we allowed few texts. And the push was few texts. The kernel didn't use priority inheritance. But the priority inheritance few text, that was us. That was this in 2006 in 2618 kernel. The Linux kernel version of priority inheritance was added this September in 612. This was needed. So now the real-time Linux when you enable real-time Linux, the kernel itself has priority inheritance. This is where I said, this is where the Ingenuity or the helicopter could use this, because priority inheritance is now built into mainline Linux when you enable the preempt real-time kernel. So to give a brief history, I think it was like 1997, was it? The Mars Pathfinder. I think you guys might know about this. It's so funny because I mentioned this in my 2007 talk at OLS, the Mars Pathfinder talk. It's just so nice giving the same talk at NASA. And for those that don't know what happened, it's on its way to Mars when the system locked up. And they had no idea what was happening, so you had to download. This is from what I understand, so I might be wrong with this. So I might be corrected here. It's weird talking to the experts about their stuff. Anyway, it's off on the way. It locks up. They check, and I guess what happened is this: you have 3 processes. You have like your normal process. I guess it was like a logging. Something was doing logging or something. like that. And then you have like a high critical process that's going, but they share the same lock. I guess maybe transfer the logs or whatever. They share the same lock. So, process C is a low priority and it's going and it grabs the lock and then it gets preempted. And then process A comes and then it goes to grab the same block that C has, so it blocks. So then C goes back on and starts running again. But guess what? A middle process that's higher priority than C, but lower priority than A, preempts C, and now it goes on. Now C can't run; it holds the lock, blocking A. This isn't what happened in the Pathfinder, but I always like to give understanding. Let's say A is the one that's going to stop B from running. Let's just say that. If A is blocked on B, it's never going to stop A, or sorry, if A, is blocked on C, it's blocked on B, A will never stop B running and it runs forever. So this is called an unbounded priority inversion. Bounded priority, people say priority inversion is bad. No, I just say unbounded priority inversion is bad, which means that you can't measure how long the priority inversion will last. Every system has a bounded priority inversion. In fact, that little part where you can see, here, yeah, the little part where you use this here, even though if it wasn't preempted, that's a priority inversion. Whenever one task is waiting on a lower priority task, but that's okay as long as there's a way to get out of it. What priority inheritance does was, if you notice C is green there, it means that when A got blocked, it gives its priority to the owner of that lock. So now C runs as the priority of A. So when B wakes up, it can't preempt C because it now has a priority of A, and C finishes, releases the lock. Once it releases the lock, it loses priority. A gets to run and then sleeps, and then B gets to run. So finally, what's the status of real-time Linux? As I said, it's done. Almost. So it got into the Linux kernel. That was, like I said, that was our main thing. That was our push. That's why, ftrace was created, because I was going to say, hey, let's do the low-hanging fruit of getting the tracing utility inside the real-time patch into upstream. Every time something goes from the real-time patch to upstream, it gets like 3 or 4 rewrites, believe it or not. We just keep pushing. And it ended up turning into ftrace, and then it just became huge. I was only supposed to be a 3-month project. I'm still working on it. So it finally made it to 6.12. By the way, but if you want to use it, don't use the 6.12 kernel. Use 6.13. Why? Because it's missing need reschedule lazy. Now, this is something that we've bought with too. Preemption's great, but the problem with preempting too much, you could hurt performance. Now, what we found out was on large scale machines, normal non-RT tasks were taking a long, or were the performance of non-real-time tasks was horrible. We're like, what's going on? Why is it? And then we traced it, and we found out what was happening was because the kernel's so preemptible now. When the normal, sched other task, when the timer would go off and say, let's preempt this guy, it would preempt it, not caring if it's holding a lock or not. So it would preempt while holding a lock, where the non-preempt kernel would not be able to preempt, and the locks would be released before it could be preempted. Now we're preempting things like crazy while holding locks. So once you preempt something while it's holding a lock, you just created the time it holds that lock to a much longer time, which then cascades, because now more things are going to be blocked on that lock. And you just saw everything is just stalled. The system's just stalled. And it was almost like you had this large CPU and almost running like a single CPU thread, because everything was being serialized like that. So Thomas created this thing called need resched lazy, where when the interrupt would go off, it would say, does this task have a lock? If no, set need resched lazy. And it will not preempt until it releases the lock. If it has no more locks, it says, hey, need resched lazy set, go and preempt me. Now that only is for sched other tasks. If a real-time task wakes up, it sets need resched and preempts it regardless, without prejudice, saying, boom, preempt this, regardless if it's holding a lock or not. But sched other tasks, normal timing tasks, would not preempt and actually turn the performance back to pre-RT, without non-RT in it. That's why this code, I don't know if you heard, watch the preempt auto things, or that was that auto, or dynamic auto things. Well, that is how, that logic is how we got to preempt lazy in. So it's dependent on that. So that wasn't ready when everything else was ready. We got print-K done, and then we got it in. We realized, wait a minute, we don't have this need resched lazy in there, but the preempt auto was how we got it in. So 613 was added in 613 for the dynamic lazy stuff. So that will bring the performance back. So I'm really nervous that people will say, hey, preempt RT is on, and everyone enabled it in 612. And then they say, wow, the performance really sucks. Let's turn this off. I'm like, not very good marketing. It's, what's it called? First time. Yeah. So anyway.
Steve,
Yeah. Yes.
real quick.
Yeah.
So how much, if any, late net? How do I say this? How much does that affect latency, if at all? That schedule, reschedule latency?
Oh, wait, latency when for what? A real-time task?
Yes,
None.
none.
Because when a real-time task wakes up, we set new reschedule. Which, okay, so when the kernel comes out, if it's reschedule lazy, it doesn't schedule, it doesn't block it. And it just goes, that's only for when you release the locks or go back to user space, then it checks if that's locked or that's held or not, then it does scheduling. But when a real-time task wakes up, it just sets need resched, and it just follows the normal path, regardless of need resched lazy there or not. So it doesn't affect the real-time side at all. This is only a non-real-time performance benefit.
Make sure, thank you.
So will this fix sometimes with the real time now? You get like errors where it's like holding lock while sleeping or something? Or
That's what this fix?
yeah.
No,
Okay.
that's a bug.
Okay.
Those are bugs.
Okay.
They need to be fixed. That's actually from when I talked back before, a lot of people saw the real time, that's usually where you have a raw spin lock, a spin lock being grabbed while raw spin lock is being held. That's what those are.
Okay. Yeah, this would be like sometimes dry.
Yes.
Just kind of.
Yes, that's where that's coming from. Where someone's like, oh, I'm gonna use a raw spin lock, not realizing what it is.
Okay. Gotcha.
I
So,
got a question.
yes.
With this last mechanism that is get lazy that we put, aren't we risking to mask a lot of sleeping context and sleeping invalid context?
Okay, so this has nothing to do with the invalid context. I think that's kind of the question that was asked here. That has nothing to do with the sleeping while invalid context. That the invalid, because then it's the RT, it'll give you that, if you enable lock depth, you'll get that. So it might actually it'll hide the bug. If anything, this will hide the bug. It's not the bug, because when a real-time task wakes up, it will preempt it anyway. And then you get the sleeping while in non.
Yes, but
Or
because some tasks are not preempted during while they holding locks. This is less likely to happen.
yes, it's less, like I said, it will hide the problem, but doesn't fix it.
Yeah, not fixed. I were saying that we are hiding a lot of bug and they may.
Not if you have lock depth enabled. Enable lock depth and it will trigger as soon as the situation occurs. So, yeah, lock depth will trigger it, regardless of whether it gets woken up or not.
Okay.
So anyway, status of real-time Linux. Remember, okay, so the real-time patch, I think, had up somewhere like 800 patches in the patch. By the way, we actually held KVM. KVM went through the real-time patch as a development tree. People don't realize that. I mean, we started in 2004. A lot of things where this is, I forgot what it was. But anyway, this slide is the diff between what's in upstream and what's in the mainline kernel. This is it.
That's the full commit count.
That's the full commit count right there.
It's down.
I did the diff. I did, if you look at what I did up top, I said git log pretty one line of brief commit, reverse 613 RC1 to the top of tree of 613 RT. So the first one here is what's called, oh yeah, module loading. There's a little thing when you have the module magic, knowing whether or not this module's I know I've tried almost done. The module, I have like one more slide. Module's done, what's it called? Module loading, you get errors, whatever. There's a bug in that. That's fixed. The next one is some serial console has some stuff that we fixed. This is just general cleanups that have to be done. I-915 is a mess. We have a bunch of hacks to fix it. This is ARM 32, not 64-bit. So 64-bit is fully supported. This is the 32-bit ARM, has a bunch of hacks to fix it. If you want to use it, it's sort of same thing for PowerPC. There's a bunch of hacks for PowerPC that fix that are not pro. Like I said, we are very strict about what goes up in the mainline. And this is just this is a thing that we added to say, hey, by the way, you're running a real-time kernel. But this is basically a proof of concept right now. We haven't figured out what exactly is, but that's it. That's the whole thing. For actually a couple more slides. So this is who's running. By the way, our maintaining. This is more like the game the guts why you want me to be here anyway. This is like the maintainership for what's going on right now. By the way, I'll push these slides up when I'm done so everyone can have it. This is actually a copy from the real-time Linux wiki that we have. I just copied what we have here. So so if you want to take it, but this is, by the way, if you notice, everything's coming up. 419 this month, we're done supporting it.
The
So
note
if you're,
came out this morning.
what?
The note came out this morning.
Okay, yes. So next one in 2 years right now, and basically if Greg decides to extend something, we're probably not going to. We're done. This is it. This is it. This is basically hard coded. If you want help, you could actually, if you want one of these kernels to be supported longer than these dates, we'll be happy to teach you how to support it.
Or appoint your people that you can pay to support it.
Yes. I don't even know if I know anyone.
I think the Red Hat folks will.
Well, okay.
They're not all we want.
That's
So-
what you want to.
So it's done. Almost. Growing pains. And I feel like we got into Mainline and I feel like that dog that finally caught the car. Like, what's next? What do we do? There's a lot of questions to handle. We have no maintainers file. How do you, like, when someone has a bug in real time, how do they know who to talk to? We have to figure out, because it's not a file. We own the whole system. So we created Linux RT users there. We did create a Linux RT devel we just created that to do that. And we need documentation.
Documentation.
Yes, this is our biggest issue. Yes,
Well, and John Ogden is also working on a neat tool to show you like what mistakes you made at writing your app.
oh, okay, I didn't know that. Oh, yeah, no, I did know about that.
Yeah.
Okay, I didn't understand what you said it. No, because he gave a talk about that at the one of the real-time workshops.
Right.
Okay, yeah. So I know this is the last,
Question on the few slides about.
Which one?
specifically This one.
oh,
So say if I write a patch that would impact the real time, right?
Yep.
So, and I run get maintainer on that patch. So basically this mailing list, I mean, unless I know
right.
that I need to explicitly add it,
That-
then will pop up, right?
If you notice, no maintainers file. We
Right.
don't know,
So-
like, how do we solve that?
Oh, well, no, you add a maintainer entry anyway.
We do. We actually have
Oh,
one.
you have one? Oh,
We have maintainers for real time, and this
You
is
just
in there
don't-
for,
you just don't
oh, yeah, so we do have a real time patch. We did update it, and of course, somehow they put my name in there.
Just for the line scope, just put the whole kernel.
Yes, we get every single patch in there, no. So the idea is, because most people won't even know to talk to us, but hopefully they'll go to their distribution, and the person's like, this is real time, I have no idea how to do this to real time, and go to the maintainers and say, oh, there's a real time entry here. Yes, we actually submitted one. I think 613 actually has a real time maintainers. I think Sebastian and I are in there. So, anyway,
There's a question on chat.
okay, I don't, someone read chat?
I can read it out. So the Linux real-time has fixed the biggest problems in the kernel regarding scheduling, locking, interruption, but Linux also has behaviors for resource allocation and management that are undesirable for real-time operation. One major issue is deferred page allocation. For example, allocate on write, not on request. Have there been discussions of tackling these issues?
Not that I'm
Not
aware
by
of,
the funding group.
not by the funding group, nor has it been brought to our attention, but we'll take patches.
So the risk of starting a civil war here, kind of touching on it, as a user, is there now any disadvantage using RT Linux going to space mission versus like traditional RTOS?
I said the only, okay,
Size of the
disadvantage,
code.
what?
Size of the code.
It's the size of the code, yes. Testing, well, we're also working on that's talking about safety critical. Now you're going to quality versus the quality measurements, which there's lots of that, talk to her, Chuck. They're working on solving the quality side of the Linux. The design side, no, but there is, if you have matters what your system is. I've given talks several times saying, real time is hard. Because you really have to understand what RT gives you is, full kind of control of your system, but you need to understand your system to know what the requirements are. And yes, I can't answer that as yes or no. It maybe is the best I could get you. So you have to understand the full scope of your system to say yes. It matters how much power you have, what's your minimum. If say like for people have like millisecond requirements, like hard requirements for millisecond, we blow that away. We actually can do full things and we have no problem with that. If you're talking, but some people say I have a 2 microsecond minimum. In a lot of cases, we can't solve that. You might need a microkernel. You might need that. In fact, I've never been against microkernels. I just saying that there's a huge, they say microkernels have its niche slot. And I always say use the best tool for the job. And this microkernel could be the best tool for the job, or other RTOS is the best tool for the job. But there's a lot of jobs out there that real-time Linux could really be solved, where it could solve the user.
So, I saw, but I'll let you guys go.
There was always
Yeah.
lots of questions.
Last question.
ahead.
At this point, I can't remember.
There you go, Zach. Yeah.
My question was around like areas in the Linux kernel that we have to do still extract caution maybe. I was looking, and you mentioned Rostedt and stuff with the eBPF the other day. And still uses Rostedt, locks, and it has its own priority.
We're working on that.
Okay.
Yeah, there's still bugs there that eBPF is, don't use eBPF if you expect real-time behavior.
Okay. All right. Yeah, I was curious. That's probably a bunch.
Okay,
Any others?
I'm sure there is.
Yeah,
Yeah, okay, so I guess I
think so. Thank you very
Yep.
much.
All right. People, there's one more question on chat.
Oh.
Maybe Steve, you can help answer
Okay.
between sessions.
yeah, while he's setting up.
You can do that while I'm setting up.
Okay, what's the check?
Does anyone know the name of the talk for the RT checker application, or which workshop it was at?
Oh, the RT checker. It was in the
Well, I know they talked about it in Prague in 23
yeah.
at the real-time
Yeah.
Linux workshop, and those are on the eLinux wiki. So.
Yeah, so basically look at, what is it, 2023 at the
2023 real-time Linux workshop
Yeah, is that
by John Ognes.
Sounds good.
yeah, let me find that. Yep, I'll send it to you, Matt.
I know there was a project a while ago that was more like an audio or video focus doing analysis of a system, but check that out.
Yeah, there's I don't remember if John talked about that at Plumbers here.